Okay, imagine for a second that we're looking out into a cosmic nursery about 620 light years away.
Hmm.
You'd probably expect something, I don't know, quiet, serene even. You know, the slow, graceful dance of gas clouds just collapsing into stars.
Like a cosmic lullaby.
Exactly. But that is not at all what we're witnessing here. Instead, what we're looking at is, well, it's violence. It's unprecedented, almost shocking violence.
It's the sound of a truly epic appetite.
That's it. That's the feeling. We are staring at a celestial object that is so young, so small, and yet it is just tearing through its environment. It isn't just growing, it's gorging.
Hoovering up material.
Completely. This thing, which we found in the Chameleon constellation, is currently sucking up gas and dust at a rate that is, and I'm not exaggerating, it's just difficult to wrap your head around.
What's the number?
6 billion tons of material every single second.
Whoa. Okay, let's put that in perspective. 6 billion tons a second. That's like pouring the entire mass of the Great Pyramid of Giza onto this one tiny object.
Yeah, but not just once.
Oh no. Every 2 minutes. For weeks on end.
See, it's an insane rate. And that speed, that intensity, is what just completely shattered the previous record for any object of its kind.
And this wasn't its normal state, right? This was a burst.
A huge burst, a dramatic spike, about a 6 to 8-fold increase over its normal kind of quiet feeding rate just a few months before. And the timing for us, for the researchers, was just incredible.
They caught it in the act.
They caught it right at the peak, around mid-2025. And they did it using this 1-2 punch of our greatest scientific instruments.
And that combination is really what makes this whole deep dive possible. We're talking about the European Southern Observatory's VLT, the very large telescope in Chile. That gave us the high-resolution data on how the material was moving, like the physics of it.
And the other half of that punch.
The James Webb Space Telescope,
Yeah.
JWST. That gave us the crucial chemical and mass context. So VLT saw the motion, Webb saw the ingredients.
Right. And this record-breaking feast, it's giving us this perfect snapshot into the most turbulent, violent infancy of a really strange category of celestial objects.
Ones we are still, desperately trying to even define.
Because what we found isn't just a hungry baby planet. What we found is an unseen, powerful force, a force we usually only see when stars are forming. And it's driving this impossible, record-shattering meal.
That's the real mystery.
That is the secret we are pulling from the sources today. We're going to figure out what allows this planetary mass object to behave like the biggest, hungriest star in the sky. Okay, let's unpack this, starting with what exactly this strange, ravenous object is and why it's giving astronomers such a headache.
All right, so the object in question has a name. It's 11077626.
Rolls right off the tongue.
Yeah. It lives in the Chameleon Eye star-forming region. Its official classification is a free-floating planetary mass object, an FFPMO.
Which is what most of us would just call a rogue planet, right?
Yeah. Exactly. Rogue planet. It's a much better name. Because, simply put, it has no parent star. It is a lonely, wandering celestial body just moving through the galaxy all by itself.
And the moment you say planetary mass, you just slam right into a classification wall, because it's not just that it's lonely that makes it weird, it's its size.
It's in that gray area.
A huge gray area. It's estimated to be somewhere between 5 and 10 times the mass of our Jupiter. So it's huge, but it's still small enough to exist in this kind of astronomical twilight zone.
That mass range is absolutely critical. For anyone listening who loves the details, astronomers have a specific, very hard line drawn in the cosmic sand.
And what's that line?
The 13 Jupiter mass threshold.
13 Jupiter.
Right. If you're below 13 times the mass of Jupiter, you are not massive enough to fuse deuterium, which is a heavier version of hydrogen in your core.
And fusion is what makes a star a star.
Basically, anything above that mass gets classified as a brown dwarf, which is essentially a failed star.
Okay, so if this thing is below 13 Jupiter masses, it's definitely not a star. But if it's not orbiting a star, we can't really call it a planet either, can we? Not in the way we think of, like, Saturn or Mars.
That's the problem. It's a 5 to 10 Jupiter mass object, and it's a baby only 1 to 5 million years old. It's still wrapped in its baby blanket of gas and dust.
A very hungry baby.
A very hungry baby. And this ambiguity brings us to the core mystery of these FFPMOs, what we're calling the villain of uncertainty.
Why do they even exist?
Exactly. If we can figure out how Chi 1107777626 formed, we can constrain its origin. And that changes the entire cosmic census. Its formation history is what determines whether it's fundamentally a star-like object or fundamentally a planet-like object.
Okay, let's spend some time on this because there are two main theories, right? And they're like completely different stories for how this came to be.
Totally. They're mutually exclusive for this object. Scenario 1 says it formed like a tiny star, or what we'd call a sub-brown dwarf.
So it was born by itself.
Yes. You have these massive clouds of gas and dust that collapse under their own gravity, right? That's how a star gets started. But what if the cloud, just runs out of steam, or it runs out of mass before it hits that 13 Jupiter mass ignition point for deuterium fusion?
You get one of these.
You get something like this. It was born alone. It followed the whole star formation process perfectly. It just did it on a much, much smaller scale.
An independent creation.
Exactly.
Yeah.
Now, scenario 2 is the ejection hypothesis, which is just way more dramatic.
I like dramatic.
This one says the object was born as a typical giant planet, a super Jupiter, inside a regular solar system, orbiting a star.
So it was a normal planet once?
It could have been. Maybe it formed through core accretion, where a rocky core builds up first and then it quickly sucks in a ton of gas.
Yeah.
But then, during the chaotic early life of that solar system, it got into a gravitational bar fight with another giant planet.
Or even its own sun.
Right. And it lost the fight. It got slingshotted out, a gravitational casualty, and it just became this lonely cosmic vagrant.
Okay, I get the two definitions. One is a tiny star that never quite made it, and the other is a planet that got kicked out of its home. But I have to ask the question someone listening is thinking right now.
Sure.
If it's 5 to 10 times the mass of Jupiter, and it's floating all alone, what real difference does it make how it was created? It's still a massive gas object out there. Why do astronomers care so much about its birth certificate?
I love that. The birth certificate. Because the birth certificate tells us about the rules of the universe.
Yeah.
It's fundamental.
How so?
Well, if it's a failed star, that's scenario 1, it means the mechanism of gravitational collapse, which we thought was really only efficient for creating big things like stars, is way more effective than we realized.
Yeah.
It means it can reach way down into the planetary mass regime.
So star formation can make tiny things too.
And it would be widespread. But if it's an ejected planet, scenario 2, that means the dynamical instability, those gravitational wrestling matches, is a common enough process to literally flood the galaxy with trillions of these rogue worlds.
And the census matters. The sheer number of these things floating around out there depends completely on which of these two mechanisms is the dominant one.
It does. And you have to remember how discoveries like this have totally shifted our thinking before. Remember the impossible exoplanet GJ3512b?
Vaguely. Refresh my memory.
That planet was huge compared to its tiny little parent star. And its discovery instantly suggested that our standard core accretion model for how gas giants form just couldn't be right in that case.
It broke them all.
It broke them all. It provided powerful evidence for the competing theory, disk instability, where gas giants form super quickly by just clumping together gas in a massive disk.
Okay, so if that other planet challenged how massive planets form near stars,
then chain 1107-7626 challenges where they form and what forces govern their growth. It's a key piece in this massive, complex jigsaw puzzle of how everything in the universe evolves.
and it's the fact that we can see it eating right now that's the key.
That's the entire clue. This thing sits right in that ambiguous zone, below the fusion limit, but it still has its primordial disk of gas and dust. Most objects, they stop growing pretty quickly. The fact that we are seeing this one actively, violently feeding right now is our chance. We can observe its baby phase physics, and that physics will tell us how it was born.
Which means we need to stop looking at its theoretical past and start looking at its very active present. Here's where it gets really interesting. We pivot now to the incredible methods scientists use to capture this thing's behavior.
Well, first, just observing rogue planets at all is exceptionally challenging.
Why is that?
They're cold, they don't emit very much visible light, and they're not conveniently sitting next to a bright star that would help us detect them.
They're just dark objects against a dark background.
Exactly. So finding one that's in the middle of a growth spurt, that's like finding a single dark marble that someone dropped in a massive sports stadium at night.
Oh, okay, that's hard enough.
And then catching it in the precise moment it decides to glow brightly.
So this wasn't just a lucky accident. The team had to be ready.
Oh, this was a targeted campaign. They were focusing on this star-forming region, Chameleon the First, for a reason. So the baseline data, they took that in early spring of 2025, and it showed Chair 1107-7626 in its quiet state. It was already accreting, but slowly.
Just sipping.
Right. But the action started in June 2025, and it peaked dramatically by August. The core data came from the VLT in Chile using an instrument called the X-shooter spectrograph.
X-shooter? What does that do?
Think of it like a forensic tool for light. It doesn't just take a picture. It dissects every single photon of light it receives. It breaks it down into a spectrum of colors and intensities.
A light fingerprint.
A perfect way to put it. And then JWST came in with its incredible infrared sensitivity.
And what did that add to the investigation?
It gave them the chemical and mass context. They used the NR-spec and MIRI instruments. MOI, the mid-infrared instrument, was crucial for two big things. First, confirming the object's mass range, that 5 to 10 Jupiter mass number, with much greater certainty.
Okay, and the second?
Analyzing the complex hydrocarbon chemistry of the disks surrounding the object. So you see the division of labor. The VLT saw the movement of the gas, and JWST saw the composition of the ingredients.
This is the moment of real scientific forensics, isn't it? They weren't just measuring how much stuff was falling onto this object. They needed to understand the mechanics of the meal.
Right. How do you feed 6 billion tons per second onto an object that really shouldn't have the gravitational pull to do that so efficiently?
That's a central question.
And that's the question that led them to the discovery of the mechanism. The whole process is called accretion matter falling onto the object. And when hydrogen gas slams into the object's surface, it glows fiercely.
So you look for the glowing hydrogen.
We look for something called the H-alpha emission line. That's basically hydrogen gas screaming and announcing its violent arrival. The amount of light in that line tells you the speed of the consumption.
But it's the shape of that light that tells the real story, the one about the powerful unseen force. Let's fire up the analogy engine to explain this channeled accretion.
Okay, let's use a daily life analogy. Let's say a construction site.
All right, I'm with you. Demolition project.
Perfect. You need to dump an enormous amount of rubble onto one small specific spot on the ground.
Okay, if I just use a normal shovel or even a big bulldozer, that rubble is going to go everywhere. It's going to splash all over the place. It's inefficient, it's slow, and it covers a wide area.
That is exactly what typical accretion looks like for a weak object. It's messy, it's haphazard, and it's governed only by weak gravity and friction in the disk.
But this thing isn't using a shovel.
No. Now, imagine you hire a specialized contractor who has invented a giant, invisible vacuum cleaner with an internal organizing system.
Okay.
This system grabs all the rubble from the entire work site and, using an invisible magnetic force field, it funnels it through a series of narrow, organized tubes. It forces all that rubble to land in two precise tiny spots, and it does it incredibly fast.
That invisible, highly organized system, that's the magnetically channeled accretion?
That's it. The object's powerful magnetic field acts like a gigantic, invisible funnel. It grabs the electrically charged gas, the plasma, from the inner edge of the disk.
So it's not just waiting for gravity to do the work.
Not at all. Instead of letting gravity weakly pull it in, the magnetic field lines act like physical ropes. They channel the material at super high velocity, forcing it to crash down right onto the magnetic poles of the planetary object.
And that's a whole other level of force.
It's where the physics gets mind-bending. Because for something that's only 5 to 10 times the mass of Jupiter, generating a magnetic field strong enough and organized enough to dominate the whole process.
To overcome everything else.
To overcome the viscosity and the thermal pressure. It's completely unexpected. That kind of organized power is the hallmark of young forming stars, T-Tauri stars specifically.
So how did the VLT's X-shooter prove that this invisible magnetic funnel was actually there and active? What was the spectral receipt for the funnel?
They looked for the definitive hallmark, the smoking gun. It's called the double-peaked H-alpha profile with redshifted absorption.
Okay, let's pause and really unpack that term, because that is the whole case right there.
It is.
Think of the light profile from that glowing hydrogen, the H-alpha, as normally just being a single simple hump, a single peak.
Right.
But when this magnetic funnel is active, the gas is being slammed onto two very specific points, the magnetic poles at super high speed. And that dual impact broadens the light emission, giving it a noticeable double peak shape in the spectrum.
Exactly. 2 impact sites, 2 peaks.
And the redshifted absorption part is even more compelling, right? Because that tells us the material is actively moving down those ropes.
It does. When astronomers talk about redshift, they usually mean the light from an object is shifted toward the red end of the spectrum because the object is moving away from us. But the term gets a little tricky here because we're talking about absorption.
Right, because the light is coming from the impact site on the planet's surface. But that light then has to pass through the fast-moving gas that is still falling down the funnel toward the planet. And since that infalling gas is moving away from our line of sight just before it hits, it causes a little absorption dip, a shadow that is shifted toward the red end of the spectrum.
That is the perfect explanation. That red-shifted absorption feature is the shadow cast by the gas ropes, the magnetic field lines, on their way to the surface. It is definitive proof that the high-velocity material is flowing along those field lines.
It confirms the magnetospheric channeling mechanism is active and driving this whole accretion burst.
Which is star-like behavior, pure and simple, observed in a planetary mass body.
The confirmation of that double-peaked signature provided the answer. Chi 1107-7626 is fueled by stellar mechanics.
It absolutely is.
Yeah.
But the sheer magnitude of the accretion rate that resulted from that mechanism, that's what elevated this from just a fascinating discovery to a truly record-breaking event.
Okay, so let's put that rate, 6 billion tons per second, into a bit more astronomical perspective. What are the normal growth rates for objects in this category?
Typically, when we measure the accretion rates of what we call embedded protoplanets, so giant planets still forming inside a star's disk, they're tiny.
Like how tiny?
We're usually talking about accretion rates closer to 10 to the minus 9 or 10 to the minus 10 Jupiter masses per year. It's a trickle.
And what was this one measured at?
Chat 1107-7626, during its burst, was clocked at roughly 10 to the minus 7 Jupiter masses per year.
Wait, okay. That means this little rogue planet was feeding at least 20 times faster than any giant planet embedded in a star's disk that we have ever measured.
At least. It's not even in the same league.
So if typical Jupiter-sized planets are using like a teaspoon to drink their soup, this rogue planet has attached a fire hose to its magnetic field and is just vacuuming up the entire bowl.
It's a total efficiency paradox. It's small, but it's the fastest feeder in the entire cosmic nursery.
It genuinely challenged the observational limits.
It did. But the speed wasn't the only shocking factor. The duration of the event was just as important in classifying it as star-like.
Right, you mentioned the burst lasted for at least 2 months, from June to August 2025. Why isn't that just, the planet rotating, like a hot spot coming into view?
That's a great question. If the change in brightness and accretion was just due to rotational modulation, so a hotspot rotating into view, it would only last for a few days.
Why?
Because the typical rotational period for these young substellar objects is somewhere between 1 and 4 days. This burst lasted for at least 15 expected rotational cycles.
So that's like discovering a flare on our sun that doesn't just dissipate after a few minutes or hours.
But instead lasts for 2 straight months, continuously pumping out this extreme energy.
It's a completely different phenomenon.
Precisely. This long duration, combined with the fact that the object's optical light increased by a factor of 3 to 6, it all pointed towards something much deeper than just rotation. It fits the profile of an Exor-type burst.
Exor. That sounds like a technical designation. What does that mean?
Exor bursts are long-lasting, high-amplitude accretion events. They're named after the prototype star where they were first seen, Lullaby.
And what kind of stars have them?
They are characteristic of young, pre-main sequence stars, like the T-Tauri stars we mentioned, that are still in the process of gathering up their final mass. During an Exor burst, material kind of builds up in the inner disk until some instability, thermal or gravitational, triggers a catastrophic infall event.
A dam breaking.
A perfect analogy, a dam breaking. So what we're seeing is that CHA 1107-7626 isn't just using a star's feeding mechanism, the magnetic channeling.
It's also experiencing a star's growth pattern. The Exor burst, it's copying the star recipe perfectly.
And we even have archival data that supports the idea that this isn't a one-off event. Spectroscopic observations from years before showed elevated accretion levels, which suggests this is a potentially recurring thing.
So it cycles through these quiet periods and then these spectacular, months-long Exor-like rampages.
And that behavior had simply never been validated in a planetary mass object before, ever.
Okay, so beyond the sheer mechanical violence of all this accretion, the energy release must have just dramatically heated up the immediate environment, right? Did the scientists find evidence that the burst actually chemically altered the disk itself?
They did. And this is where the JWST MARI data deliver the knockout punch.
The ingredients.
The ingredients. Pre-burst observations confirmed the disk was rich in carbon compounds, hydrocarbon emission lines, specifically methane and ethylene, CH4 and C2H4, the basic building blocks of organic molecules.
And those are the standard things we'd expect to see in a cold planet-forming disk.
Correct. But during the peak of the burst, the energy released at the poles heated up the innermost disk, and they detected an entirely new signature.
What was it?
Water vapor emission at a wavelength of 6.6 micrometers. And this feature was completely absent when the object was quiet.
Water. So the magnetic funneling didn't just move gas around. It actually generated water by injecting so much energy into the cold disk material that it heated it up enough to create and emit water vapor.
It's the first time accretion-driven chemical changes have been observed in real time in the disk of any substellar object. We see this process in young stars like Lullaby during its bursts, but never, ever in a rogue planet.
It's incredible.
This single observation provides validation. Even the smallest, loneliest objects that are following the star formation path can trigger the volatile, energy-intensive processes you need to create complex molecules.
Including the one crucial ingredient for life as we know it.
Exactly. It's a chemical confirmation of stellar behavior. This planet mass object is a miniature star-forming system in every single sense, except for hydrogen fusion.
So, okay, let's review all the evidence. We have an object between 5 and 10 Jupiter masses. It's free-floating. It uses magnetic channeling to sustain a record-shattering accretion rate. It undergoes star-like Exor bursts, and it chemically alters its own disk by producing water vapor.
That's the rap sheet.
So where does this leave our original mystery? Failed star gravitational collapse, or ejected planet dynamical instability.
The pendulum swings, and it swings heavily toward the failed star or sub-brown dwarf interpretation.
Why so definitively?
Because the physics that you need to generate and sustain that highly organized magnetic field and to drive an Exor-type burst, that's intrinsic to the gravitational collapse formation pathway. It's part of the package.
And if it were an ejected planet, what would we expect to see instead?
Well, if it was violently ejected from a star system, it might retain its magnetic field. Giant planets definitely have them. Jupiter's is famously huge.
Right.
But that magnetic field wouldn't necessarily be aligned or powerful enough to dominate the disk interaction and produce a sustained Exor-type burst, years or millennia after being flung out.
The system wouldn't be stable enough.
Exactly. The sustained high-amplitude channeling points directly to a process that's inherent in its birth as a solitary gravitationally collapsing body.
This single discovery, then, it really challenges our definitions, doesn't it? We use that 13 Jupiter mass deuterium burning limit to separate stars or brown dwarfs from planets.
It's our neat dividing line.
But if an object at 5 Jupiter masses is using the exact same physical mechanisms, the magnetism, the accretion bursts, as a protostar, aren't we blurring that distinction almost into non-existence?
We absolutely are. It implies that the gravitational collapse process, the one that creates stars and brown dwarfs, can operate far more efficiently and at much lower mass limits than we previously assumed.
It proves that the formation environment collapsing alone in a dense cloud is more important in determining the physics than the final mass of the object itself.
That's a great way to put it.
So the census of rogue planets just got a whole lot more complex. If the star formation mechanism can produce objects all the way down to 5 Jupiter masses, there are potentially millions, if not billions, of these tiny failed stars wandering the galaxy that we haven't even cataloged yet.
And that matters. It matters because it affects everything from our models of stellar mass distribution to our predictions for future planet detection surveys. If a large fraction of these FFPMOs are failed stars, they're fundamentally different from ejected planets in terms of their composition, their internal heat, their longevity, everything.
But finding these things is the hard part, as you said, because they're so faint. So how is the scientific community adapting to the challenge of finding more of these stellar imposters?
We're relying on the next generation of instruments, things built specifically to overcome this faintness limitation. The current bottleneck is sensitivity, which is why the European Southern Observatory's upcoming extremely large telescope, the ELT in Chile, is so anticipated.
The ELT, they call it the world's biggest eye in the sky.
And for good reason. With its massive main mirror, it's going to collect exponentially. More light astronomers will be able to probe fainter objects at greater distances and with higher resolutions than ever before.
So we'll just be able to see more of them.
This telescope is expected to completely revolutionize our ability to not just find, but to study these isolated, lonely worlds in detail. We'll finally get enough statistical data to see how many FFPMOs are failed stars and how many are gravitational escapees, we will finally resolve the great mystery of the rogue wanderers.
It's just awe-inspiring to know that by focusing on one tiny, unusual object 620 light-years away, we have fundamentally shifted our understanding of creation.
It really is.
This discovery validates the joy of focusing on the exceptions, the impossible planet, or the hyper-accreting rogue. It proves that one unusual observation can redefine the physics that governs the entire cosmos.
And it makes you wonder what else is hiding down there, just below that 13 Jupiter mass threshold, just waiting to have its star-like behavior exposed.
This has been an incredible deep dive into one of the most exciting recent discoveries in astrophysics. We traveled to the Chameleon constellation to find Chattel 1077626, a planetary mass object consuming gas and dust at an astounding rate of 6 billion tons per second.
And this record-shattering growth isn't driven by typical planetary mechanisms. It's driven by a star-like, invisible magnetic funnel, which was confirmed by that specific spectral hallmark of channeled accretion.
And this process forces the object to behave exactly like a protostar, experiencing Exor-type bursts and chemically transforming its own surrounding disk by creating water vapor.
The conclusion is just profound. This free-floating object is most likely forming via gravitational collapse. It's extending the star formation process down to masses far lower than we ever thought possible, blurring that strict definition between stars and planets.
It's a spectacular view of creation in progress, showing that even the lowest mass products of star formation have a turbulent active infancy full of these violent energy releases.
A whole new chapter.
And this leaves us with our final provocative thought. If this object, which is barely larger than Jupiter, is successfully following the star formation recipe, and that comes complete with a large, chemically rich accreting disk, is it possible that this free-floating sub-brown dwarf is already creating its own system? Could Che 1077626 be actively forming miniature planets from its own disk material? If the magnetic fields of these rogue worlds are so powerful, what miniature isolated solar systems are being born right now, floating alone in the dark, fueled by these gigantic invisible magnetic funnels?
That is certainly a complex set of worlds waiting to be found.
Indeed. Thank you for diving deep with us today.